autonomous vehicles are said to be able to generate up to 3,000 gigabytes per hour of data. So this is a huge amount of data, and we have to find a new way to store it. And this is a big problem also for global emissions. Just imagine that it should be 8% of the global emission only about storing data in 2025. So we have a need for more efficient data storage solution. And as I've said, this is the old thing in molecular magnetism. And molecular magnetism is a quite old story now, but we are still innovating. That is based on single molecule magnet, single chain magnet, and spin crossover compound mainly. There is also other stuff. We can put them on surfaces. We can make a nanoporous magnet. We can also try to do sub-Kelvin nanocoolers, spintronics, quantum computing, a lot of luminescence, and characterize the magnetic activity of MRI agents. These are only examples for sure. You have probably seen very recently the very nice work of Corinne and Rodolphe about MOFs and in molecular magnetism. So this is all the thematics that we can address with molecular magnetism. And for this talk, I will focus on doing molecules and trying to put them on surfaces to make devices. So also for the youngest people from the audience, the main difference between single molecule magnet and single chain magnet is in their relaxation process. They are governed by an Arrhenius law altogether, but the physics that is behind is totally different. And main driving things are Orbital relaxation for the single molecule magnet, at least we hope, but there is also a lot of different relaxation pathways, and I'm sure that Nick will present this very deeply after me. On single chain magnet, we have also an Arrhenius law dependence, but this is 1D relaxation, so this is totally different. And there is the advantage to have no parasite under barrier relaxation in this kind of system. This is why we are interested in trying to build new single chains. There is a lot of different single chains. These are only small examples. You can synthesize them with a very large library of organic ligands, paramagnetic ligands. You can do it with 3D, 4F, 3D, 4F ion, whatever. So you just need anisotropic centers, and to be sure to shield magnetically the chains, to be sure that your magnetic behavior is confined inside the chain. So what we are trying to do now is to control the size, the morphology, and the purity of our single chain magnet microcrystallites. So why are we doing this? Is because this is a work that was driven by Quentin Evra. A compound adapted for surface deposition is quite different from the ones that we use in traditional squid. We are not picking a crystal in the middle of a Moser solution and trying to put it in a squid and so on. We need powders with high purities, accessible in large batches to be able to perform comparative tests of deposition. Because when you do 20, 30, 80 tests of deposition, you have to be sure to start from the very same material. And we need also a small crystallite size distribution to have an homogeneous behavior towards solubilization or sublimation or whatever the techniques that you use to put your compound on surface. So this is a serious problems for extended molecular networks because they are much more difficult to purify than 0D compound and to solubilize, obviously, because of their infinite nature. So we've tried our approach on a model system, a very old single chain magnet that we made a long time ago, made of terbium, beta decatonate here, and radical ion here. So our approach was to do the classical synthesis. This is very, very simple coordination chemistry. We use terbium beta decatonate, we use our radical, and we mix it together, and usually we get our chains. And now we try to use the ultrasonication, but in the ultra crystallization scheme. I will explain it right now. And we also perform control sample to check the difference between the two approaches. When you do a standard crystallization, this is the temperature here, the time, and the follow of our crystallization process. You can isolate your samples, and on the S samples that we call S because short, on the short crystallization period, 5 minutes, we can see this kind of crystals. For 24 hours on the long crystallization, we see bigger crystals, and you can even see here some white spots here. If you compare this by counting on 400 crystallites of SEM analysis, you can calculate the aspect ratio of your sample, and it's a polydispersity index. It's PDI. PDI should be below 0.3 to be reasonable for surface deposition. What you can see is that on sample S and even on sample L, we have very high PDI value in width or in length. So it means that we have a huge polydispersity of the length and width in our sample. And we don't like it to try to go further in the surface deposition. So a strong crystal size distribution. We can also observe in our systems polymorphs. So we have the chains that are these crystals, and we can even see monomers, two kinds of different monomers that are basically only one lanthanide and two radical, and these are much more robust and much more stable than the chains. So very easy to get this kind of compounds. And you can even have traces of unreacted terbium ion. So this is very easy to see on our terbium beta decatonate because this is highly luminescent. But if you move for other non-luminescent lanthanide, you should have the same traces. So we have many problems to put these chains on surfaces or to be clean enough to go towards surface deposition. So what we have done is that we have sonicated with a high power sonicator our crystallization media to try to gain in size control and purity on our crystals. So high power ultrasonicator is this kind of instrument. You have here a big plastic box, otherwise you lost your hearability after 1 minute. Make a lot of ultrasonic noise. You have different horns here, and you have to tune a lot of parameters to have a good sonication, good bubbles inside, and so on. Let's say that to make a long story short, you use a pulse mode, otherwise you make your solvent boiling. And we are delivering for this study 50 watts per pulse per second in our system. So we perform 3 different sonication that we call US1, US2, and US3, and a silent crystallization that we call T, that is a thermally assisted crystallization to reproduce the heat that we have in our US sample, but without the shock wave inside. So we have two effects of high power ultrasonication. The first is about mechanics, killing the first crystal germs by the shock wave. So it means the compound wants to crystallize, but we kill everything that starts crystallizing. So this kind of a delay before crystallization. And a thermodynamic effect that we are creating hotspots in our system that highly favor a chemical reaction. Even if we are at, you can see here, 56 degrees, so this is not very high as temperature, but locally you have very high energy, so you can favor crystal chemical reactions. So what we can see is that even on the very first sample, when we deliver 75 kilojoule, we see a very good PDI of 0.2 in width and 0.36 in length. And as soon as we get further, we see this PDI that is going below 0.2, as that stabilizes a little bit. And you can see here that basically we should have needles, but we are doing round crystals because the shock wave cuts the needles and cuts the edges of all the crystals. So we have very good polydispersity, and we are making round things. If we compare with the thermal silent condition, we see totally different things. Just imagine here that the scales is multiplied by 10 in length and in width, and the polydispersity is very, 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 very big. So this is not an effect of only putting a thermal plateau in our crystallization. This is an effect of the shock waves that we put inside that disturb the crystallization of the sample. So this is quite uncommon for us, for coordination chemists, to say that we get better crystals putting ultrasonication, because usually we are doing sonofragmentation. That means that we try to avoid smaller balls of powder in a solution or things like that. This is sonocrystallization. This is quite different. And since we are performing the sonocrystallization since the very beginning of the reaction, we are doing also at the beginning a kind of sonochemistry. So sonochemistry at the beginning, sonocrystallization in the middle of the reaction when the crystals appear. And this is different from sonocrystallization, just to be clear for everybody. So we just check our sample. Obviously, we see a very nice crystallinity of the powder. So a better crystallinity when compared with the standard compound here with the thonicated. We see disappearance of the traces of free terbium building blocks that we can easily see in luminescence measurements. So we see the characteristic line shape of the terbium, and as soon as we sonicate, these peaks are vanishing. So we are losing the terbium traces that are big problems when trying to put the powder on surfaces. So we have a cleaner and cleaner sample. And then on the magnetic point of view, no change at all. So we keep the single chain magnet behavior. So we have an increased crystallinity, purity, and a magnetic behavior that is preserved. So we were quite happy about this approach. So just let's try to put this on surfaces. So we've tried to put our chains, sonication, aging, I mean, standard surface procedures, and to do AFM images. What we observed is that we get kind of fractal since we have a still solvent on our sample. These are deposited on mica surfaces. And here we can see a very nice organizations of 1D molecules, and that are organizing along the mica edges. So if you do the Fourier transform, you can nicely see these 1600 degrees. And we are very, very happy. And when we are doing this, we do just make a test sample, control sample, using your starting materials. So we check with the free radical. We don't observe anything. And we check with the terbium beta decatonate alone, and we observe exactly the same thing. So this is only the chain that breaks. So this was very unfortunate. We are just depositing chains of terbium beta decatonate on surfaces. This means that this process of deposition is not adapted to our chains, and they are not robust enough to preserve by this process. Okay, we have nice powder at the beginning, but the deposition process is not adapted. So we change a little bit our mind and say, okay, the crystal packing and the chains are not strong enough to be deposited on surfaces. Can we tune this a little bit? So we try to make chains strong enough for surface deposition. So this was a work performed by Felix Wars that is finishing his PhD now in the lab. And we tried to add an aliphatic chain on a neutral hydroxide radical. So this is extremely simple chemistry. To have a better interaction with selenized surface, because these kind of chains are known to better interact with all the surface that we are using, and adding degrees of freedom to our system to create new crystal packings and see what happens. So we obtain these nice crystals. And the first parameters that we get from the diffractometer were quite surprising, because we obtain a very big cell volume. That is not used. Usually we just have things with one terbium ion and one radical in a unit cell. So we have much shorter cell volume. So this kind of cell is a little bit strange. So when you look to the asymmetric unit, actually we found that we have 2.5 radical and 3 terbium ion in our asymmetric unit. So this is mainly because the aliphatic chains are moving everywhere and add degrees of freedom, and so you have an increase in your asymmetric unit. So just have a look at it. When we try to analyze our structure, we've seen that we have something that is rotating, that a chain with a 20 nanometers pitch length. We have 12 asymmetric units that make a chain rotating when we observe our crystal structure. So it was quite surprising, and we were quite happy about it. But obviously, since the pitch length is very smooth, you have room for other things inside of this system. And indeed, you have a lot of other things, and you have other chains that are wounded to create kind of a nanotube. So we have 11 chains that are rotating with this pitch length, and we are creating a nanotube, but this is only a coordination nanotube, supramolecular, because there is no interaction between the chains, apart supramolecular interaction. There is no bond, sorry, between the chains. And this kind of supramolecular nanotube, this get chiral, because when we look at the crystal packing, we have this hexagonal crystal packing. And we just get the right-handed helix for the moment, but we can imagine to have both in our mixture. The only problem is that the crystal structure analysis is quite long because too much and the cell is very big. So we have 4.5 nanometers internal diameters, so they are quite big tubes filled with a solvent molecule. In our case, this is heptane molecules. And so obviously we have a porosity in these samples. This is a 44% porosity. Because of this porosity, when you do SEM measurement, so we have first investigation. So you can see that these are the very first measurements. These are not sonicated samples because you see a big polydispersity in the dim dimension of the chains. And from now we are sonicating everything in the lab. So we have more shorter crystals, more homogeneous. But when you do our SEM measurement, we can see that the crystal bent during the measurement because we are under vacuum condition. And as soon as we measure and try to find places and so on, all the crystals start to bend because we are losing the solvent. So the crystal is still a mechanic robustness, but obviously on the diffraction point of view, we have no signal and we lose the crystallinity. So this is quite a drawback because we don't like to put amorphous thing in a squid. We just want to be sure about what we are putting in a squid. Putting things that have not nice PXRD diagram are not very nice. So we use our knowledge of luminescence to try to be sure that what we are putting in the squid is really our genuine sample. So this is the emission of the radical alone. So this is the emission part and the excitation part. Neutral and nitroxide radicals emit in the red. Okay, they're quite hard to see at room temperature, but at 77 K we can see it easily. And when you compare with the chains, what you can immediately see is that there is a shift, signature of the coordination that is well known on this kind of radical. We don't see any free radical emission, and we don't see any terbium emission as I've shown before. That should be way more luminant than our sample. So any trace of terbium here should be giant in the middle of the spectra. So we have a pure sample that does not decompose. It just lost its crystallinity, but it's okay, and we can trust it, and we can try to do magnetic things on it. So these are the magnetic measurement. So we clearly see on the chi-T versus T divergence of the chi-T that is characteristic of single chain magnetic behavior with a saturation at low T because of the field that is too high. So then we lower the field, and we can even reconstruct the chi-T from the AC measurement. So we have a clear signature of a creation of a correlation length at low T. We can extract the value of this correlation length that is very small if you compare it to a more traditional single chain magnet based on 3D ions, for example. We are on 4F single chain magnets, so values are much more smaller that you can see on other single chain. And we don't have any anomalous behavior in a specific heat measurement. So we have no signature of a 3D order. So we are looking at a single chain magnet. So despite that we are organizing our sample in nanotubes, the single chain magnet is still observable. We can do AC measurement on it, obviously, and characterize the two regime, as you can often see on single chain magnets, the finite size and the infinite size regime. Once again, very closed value. because we are working with very small correlation energy when compared with 3D single chain magnet. So we can extract a correlation length, to make a long story short, of 5 units in our system. So we make 5 units of correlating spins in our chains. Obviously, we have to take care here that it's not a regular chain. We have an anisotropic spin, that is a terbium, and then a radical that is isotropic, and so on. So the picture is a little bit more complicated. So we measure an hysteresis at low T. So this is at 0.5 K. We measure quite decent corticity field and remnant magnetization. So we have observed single chain magnet behavior on our chiral supramolecular nanotube. So we were quite happy about this. And when doing this investigation, I can propose you an interlude, as we say in French. We have seen weird things. When we measure our samples, sometimes we found some strange hysteresis. So we say, okay, maybe this is a problem of solvation, desolvation, and okay, what occurs? So we started with a very exotic idea. So we have a magnetic sponge and a single chain magnet reactive to nanotube solvation, but because if we are looking to single chain magnet behavior, it should not depend on what you put in between the chains, because the chains are expected to be isolated. And our student, Felix, said, okay, I will just check the batches. And we in some cases, we see that batches are changing and the crystals are evolving, especially under a rainy day that you can often have during autumn in Brittany. And so we check to this kind of plates, and we observe this molecule. So this is a finite molecule where 6 terbium ions are bound together by 5 radicals, and that is finished by water molecules. So these are pieces of chains, basically. So we were quite surprised about that, and the refinement was not so easy, because imagine that all these chains are moving everywhere, and you have CF3 things here, and it was not an easy work. But anyway, we get the crystals. In this kind of compound, you have a very different coordination polyhedra, because all terbium ions are different. You have good stacking interactions, that it makes the compound is robust enough. And obviously, when you try to do the calculation, you have to have a very motivated postdoc student, because yes, you just came in the office saying, okay, I have a compound, okay, I want to have the orientation of the anisotropic axis, okay, and I have 6 in one molecule. So he's not so happy. But you can see here that all the axes are pointing almost everywhere. So no spatial orientation of the axis. And obviously, this change is triggered by the absence of presence of moisture in the atmosphere. So the chains switch to hexamers in case you have too many water in the atmosphere. And obviously, we redo the whole process by putting closed vials in water, and we immediately found the hexamers. So this is a Brittany-like transformation of chains, let's say. So just analyze this a little bit. You can see that between 2 hexamers here, we have water molecules that are interacting, a very classical picture that we can see on beta decatonate. And obviously, the calculation shows that with this terbium distance, polar interaction. So an interaction that is not strong enough to propagate a correlation length. So with this in hand, you can put it in a squid, and actually you see a correlation length, a strong divergence of chi-t. Once again, you can measure it with a 1000 Ørsted field, and then you can measure with 0 field with AC, so to be able to reproduce the full divergence. And so you can see a chain-like behavior, but on a finite molecule, with correlation lengths data that are similar, a little higher than what we observe on the chain. So when you compare the hexamers and chains, hexamer actually behave a little bit better. You can even see two regimes on your system. So it means that the hexamer are big enough because the correlation length is small enough to see two different types of nucleation. The one that starts from the middle of the hexamer, so an infinite regime, and the one that starts from an edge of the hexamer. So we can calculate the correlated unit. We can see that we have 3 units, so it fits quite well in the hexamer. And we can observe the both finite and infinite regime on a single chain magnet, but on a finite molecule. So just measure the hysteresis. So we have actually a better hysteresis that we observe on chains, probably, but we are not sure because we are saying things that is much more linear than the chains that are curled. So maybe the couplings are better. We cannot extract precisely coupling values because we have a lot of terbiums difference. We have a lot of different radicals, and on these chains we have also radical interaction and terbium interaction that actually are bigger than the terbium radical interaction. These are called next nearest neighbor interactions. So it makes those things very, very complicated, and we are not able to extract very precise value on this kind of systems. But anyway, we have been able to observe the single chain magnet behavior on the finite molecules. So this was quite a strange object, and we were quite happy about that. And we can also hypothesize that hexamer could be easier to manipulate than chain because these are only 0D molecules, but behave as single chain. So without the content tunneling problems of the single molecule magnet and so on. So these are probably a nice object to try to put on surfaces, and we are trying to do so. So closing the interlude and going back to the chains, we try to put them on surfaces. And we get this spaghetti versus rigatoni dilemma, as said by my Italian colleagues. What do we put on surfaces? Do we put an isolated chain or nanotubes, supramolecular nanotubes on surfaces? Obviously, we don't trust the spaghetti way because we have seen that the chains are not very robust. And so if we see something, it should be a rigatoni, let's say. Obviously, we are now sonicating everything. So to have a high purity powder with a homogeneous crystal size distribution. And this is what we can see on selenized surfaces. We see nicely fibers. And here, for example, an isolated fiber that is pointing here. And the dimension of the fiber, oh, my arrow moved a little bit, is totally comparable to the dimension of a nanotube. So we are quite confident that we have nanotube on surfaces, and this shows that this organization of chains into much robust supramolecular architecture is a nice way to put these chains on surfaces. And we are now looking for beam times to be able to measure the on-surface single chain magnet behavior. We have new development on this, but unfortunately we are in a patenting process, so I can. So to summarize what we have done recently in the lab, we've used high power sonocrystallization to show that this is an easy way to control crystallinity, size, and purity of our samples, and this should be extended to any techniques that require a crystal size control of powder for any kind of measurement. We have been able to show that the lanthanide radical chains are destroyed if they are used as standard chains. But once you are able to create tubes, supramolecular tube of these chains, you are able to, you can manipulate them and put them on surfaces. We have also shown that we can have alternative to the single chain by having these long linear molecules that behave as single chain but are finite molecules. And we are looking to time and beam time and synchrotron to be able to observe an on-surface single chain magnet behavior. So these are the people involved in the study, people from the lab, people from the theoretician, that help in magnetism in crystals and our inter-influence for the AFM measurements, the fundings. And I would like also to conclude by a little bit of CMM that will be next year, that will be organized in Rennes. And these are the people that will organize this, so you know a lot of them. And this will be the conference hall. And we hope, at least we see, that you have this kind of things that we don't know that much now. And we hope that we will be able to welcome you and to have a good time all together speaking about chemistry or even other things. And maybe there is also this kind of things in Mont Saint-Michel and Saint-Malo where we'll try to set on a conference trip. So this is it for my presentation, and I'm ready for a discussion or questions.
Okay, thank you, Kévin. Questions, comments, so it can be in the chat, it can be directly. If someone has a question now, you can open the mic. Nicolas, yes.
Hey, Kévin, thank you very, very much for that lovely talk. It's really interesting to see how that works come along. I have a couple of questions. The hexamers that you find, you know, when you find the chains have been cut upon hydration, what's the packing in the crystal structure of those? You said they're more linear, but I'm curious how they arrange themselves in the solid state.
Okay, I have no picture right now. We can have a look to maybe this one. So this is only part of the packing. Actually, you see that we have maybe we can call it pseudo chains, where all the hexamers are laid one around the other with this kind of water interaction. And then you have other chains parallel and another chains that are half parallel. I mean, you just translate it by half the cell dimension. So this is, let's say, a very standard crystal packing that we usually see on standard single chain magnet, except that the chains are cut and that the water coordination scheme switch two chains that should be aligned, I mean, and make it a little bit misaligned along the B direction.
Okay, thanks. And
Kévin, can I ask a question? Sorry, Nick, to interrupt.
That's okay. Yeah, go.
So it's the same thing. I mean, when you have a single chain magnet and you say the single chain is 5 units long in the case of the real chain, it means that every 5 units you have a defect. Okay, and now you are making a segment of 6, and you have a defect every 6 segments. So for me, what you call the chain and is even shorter than what you call the hexamer. If I believe what you say.
Yes, I agree because probably the correlation energy, you see that the correlation energy in the chain is smaller than what we can see in the hexamer.
Yeah, but that's not the problem. That's not the problem. The chain is cut. It's not due to the interaction, it's due to defects. If the chain was infinite, it will never start from the end. So if you have a finite size regime, it means you have a defect in your chain.
On this point,
you have a missing spin, or you have something that is missing. So there is a paradox here. What you are presenting as a one-dimensional coordination polymer, very on the crystallographic view, it's infinite, but indeed it's shorter, magnetically speaking, than your hexamer.
Yeah,
which is very, very, very strange.
Yeah, no, I mean, to be honest, Rodolphe, we made when we first get these results, we make a meeting and say, okay, let's start again and let's reconsider everything, but because we are making a huge mistake here, and we get this kind of problem of purity and say this is not the way that we think it should behave, but you're right, and this is what we observed after being sure that we are measuring the good things and be sure about the purity of the samples and so on and so on. But
so can I suggest something?
Yeah. Sure.
I mean, so let's imagine your hexamer is a crystalline version of your polymer chain. So your defect, your water defect are crystallography periodic. Okay.
Yeah.
While in your what you call the chain, this water site is actually disordered and you don't see it. So basically, you have the same compound.
We don't see it on the chain because okay,
it's completely disordered. And then you have a statistic that allow you to get the crystallography and to not see, there is no periodicity, so you don't see it. And then when you have in the hexamer, you crystallize these defects, so you make hexamer. So for me, they are almost the same compound.
Yeah, for sure.
So I am not even sure the first compound is a chain. You see what I mean?
Yeah. I mean, okay, just a thing, but we see a random thing on the first crystal structure, and then we can localize these defects on the second one that are the hexamers. It could be a possibility. Yeah, you're right.
So what I was going to ask as a follow-up here is that, in relation to the packing of the hexamer, is there a relationship between the sort of larger cell picture between the hexamer and the chain? Can you see where, the chains have maybe just been, as Rodolphe says, that you've localized defects by having stoichiometric water, where you've just cut the chains or, cut these spirals, and so you get these adjacent units. I wonder if they can map onto each other in some approximate way in a more global sense.
I mean, hexamers crystallize at P21 over N, so it's a very standard space group. And chains, sorry for, I don't want to escape Zoom. Chains are in P61. Sorry, this is not nice, but P6122, and there is no, I mean, I have not seen obvious relationship between the two.
I mean in real space, not necessarily in the space group, because the space group is, as Rodolphe says, the average of the entire crystal.
Yeah, it's an average. Yeah, I'm sure.
But in real space, if you take, a supercell of some number of unit cells in all dimensions, and just line them up against each other, do you see relationships between the hexamers and the chains?
We try to reconstruct supercells of the hexamers to make huge crystal packing and to see if we can find a way, for example, by having these hexamers, if we tilt it a little bit and we induce a pitch to have a chain, but we found no solution.
But if you look at the hexamer with the same view, do you have the same nanotube?
No.
It's completely different.
Yeah, totally different. I'm sorry, I don't. It's a pity. I don't have the images here, but you just see regular chains. There is not a beginning of a curling, no voids. There is not total. This is totally different.
Okay.
But I understand the localization of the water when comparing with the chains. Yes, you're right.
And a quick last question, if that's okay, on the last slide that you showed with the sort of spaghetti chains everywhere in your AFM. Have you thought about? I mean, I take that these are sort of recent measurements, but have you thought about perhaps dissolving or at least suspending your chains in a polymer melt or something and trying to extrude it to align your chains, your molecular chains?
Are you in the patent office, Nick?
No, I wish.
Okay. This is my answer.
Good luck.
Thank you, Nick.
Okay. We have a question from Matteo Azzoli.
Hello, thank you, Kevin.
Hi, Matteo.
I was wondering if with the sonicating process, you will be able to prepare a sufficiently big crystal in order to collect the circular dichroism for this chiral compound, or is too small?
Yeah, sonocrystallization is quite, I mean, it's very useful to have powders with high purities, but obviously since you are sending sonication waves in your crystal, you cannot grow very big crystals. And we see a limit after 3 hours of sonication, we have a plateau that depends on each system. And these are still crystallized that you can see on ACM. These are all ACM images, but they are not big enough to be reasonable, considered for other kind of on single crystal measurement.
Okay, thank you.
Much adapted to do high quality powders, let's say, but not single crystals or something like that. At least at the power that we use it. It should be investigated.
Okay.
I'm not very confident.
Do you think that by using a chiral organic chain, you can separate such type of chiral nanotubes, not spontaneous resolution, but having chiral with an absolute configuration?
I don't think for me, but yeah, I know what you mean. But for me, there is no reason that we don't get the other helix on other crystals in the batches. As the data collection are very long on the microsource, we use 1 night on the microsource to get a reasonable data resolution. And selecting crystals is also a long stuff. So we have not taken time to screen a batch and to have a statistic to see, okay, we have the right-handed and left-handed helix in the batches.
Okay, thank you.
Thank you. Another question from Maciej Kolczynski.
Can you hear me?
Yes.
Hi, it's a very nice talk. I have a question back going to this chain versus hexamer change. Did you consider that the chain might be reversibly, hydrating? There is some low barrier to removal of that water. And did you ever try to do this transformation kind of like in a single crystal to single crystal manner, meaning like you exposed the single crystal itself to moisture and then tried, pulling vacuum on it to see if you can actually get this transformation reversibly within a single crystal?
Yeah. So we've tried on single crystals on the chains, and it's failed immediately. And we even tried on powders. And on powders, you can go from chains to hexamers, but not the reverse. When you heat up your hexamers, you just heat them, and after you destroy the sample.
And this hexamer is a thermodynamic end for this, or you can even more fragment that hexamer to like smaller units, because it seems weird that this would be, like the thermodynamic thing of the reaction would be the hexamer and not some.
Yeah, I totally agree. It's very strange, and we at the beginning we say, okay, maybe we can have a huge library of compound, and it will be also on the magnetic point of view very interesting to be able to cut the chain with 10 units, 6 units, 4 units, and we make a lot of chains in the crystallization condition, and we always end with the 6. So maybe it's not, but we are not able to find other solution. I mean, as soon as you put enough water, you get the 6 every time.
All right, perfect. Thank you.
Thank you. David Harding from Thailand has a question.
Yeah, I was just sort of following up there. I wonder, Kévin, if you could use some kind of like chiral, because you said you used cyclohexane is in, the void space in the chains. If you could use something like, R-methyl cyclohexane or S-methyl cyclohexane. So use something that's almost exactly like what you've currently used, but use a chiral cyclohexane.
This is heptane. We have heptane inside the
heptane.
And we tried with other solvent because to see if we can tune the cavity and so on. And we are not able to have crystals. Maybe it's probably a question of affinity between the chains that has a C6 with the heptane, and that match well to stabilize the structure. But as soon as we change for other solvent, even aliphatic solvent, we were not able to have other crystals.
Okay, very nice.
Other questions? I have one, Kévin, regarding your sonication process. So you say that you have hot spots in your solution, so very hot, you say 5,000 Kelvin.
This is from
yeah. Is there any damage on the reactants that you put, and even on the product that you have with this kind of local temperature?
No, because you have immediate dissipation into your solution, and you see the overall temperature that you are measuring is quite low. We have a plateau at 56 degrees, so we don't have a global high temperatures. This is very localized, at least at the power that we are using. You can use transductors to make very high ultrasonication, and maybe it should be different. But on this kind of average power sonication, we don't see any damage on the samples.
Okay. And regarding the crystallinity improvement, have you checked further by making some refinements of the profile matching of your powder X-ray diffraction pattern to check the increase in the domain size, current domain size?
No, we have been lazy and we have not been until there.
Okay. Other questions or comments? Nobody on the chat. I see no hands raised. Okay. Thanks a lot, Kévin, for your talk. And so now we will move to Nick Chilton. I will let the microphone to Boris to introduce Nick.
Thank you, Guillaume. So today it's a great pleasure to welcome Nick in this conference series, and let's introduce Nick shortly. So Nick is currently a lecturer senior lecturer on Royal Society University Research Fellow at the Department of Chemistry at the University of Manchester. But before that, Nick completed his undergraduate degree at the Monash University in Melbourne in Australia, and then moved to UK and completed his PhD in Manchester, University of Manchester, under the supervision of Richard Winpenny and Eric McInnes. And then since then, he already won a lot of awards. In particular, in 2019, he won the 7th Olivier Kahn International Award from the European Institute for Molecular Magnetism, became the same year Royal Society University Research Fellow, and won several grants, and currently is owning ERC starting grant, for example. So Nick's main interests are quite large. If let's say focus mainly on molecular magnetism, but from several aspects. I would say computational chemistry, quantum mechanics, but also screen magnetometry, EPR spectroscopy, and so on. So probably we'll talk about that today, but I don't see his slides. Guillaume, do you? Okay. Okay, great. So, and today we'll mainly focus on spin vibration coupling in the magnetic molecules. So, Nick, it's a pleasure.
Sorry, I couldn't find the mute button. After almost a year at doing this, more than a year at doing this, you'd think I'd work out how to use it, but there you go. Thank you very much for the kind introduction, Boris, and of course to the Association de Magnétisme moléculaire for the invitation. It's a pleasure to talk to you this afternoon. As the introduction went, I'll be talking about vibration coupling in molecular magnets. So I will first just give a brief overview of a few of the things we're interested in our research group. So we have a number of interests across molecular magnetism, so say to the more applied side of MRI contrast agents, into the more fundamental end of actinide electronic structure. And today I'm going to be talking to you about these two aspects over here on this side. So vibronic coupling, and this is a very bad image of what it means, but hopefully I can illustrate to you what this is all about today. And also single molecule magnets and the related area of molecular spin qubits. And so this is a reasonably recent shot of the group. We've had a few comings and goings since then, and soon there will be a postdoctoral post that will open up in my group. Okay, next slide. Right, so I'm not going to labor too heavily the background of vibrations in chemistry and molecular magnetism, and I'll rather shift to the focus of today's talk quite quickly. But of course, vibrations are everywhere, right? In chemistry, you know, by defining multi-atomic constructs, you by definition have vibrations, and of course, we know as chemists that you have 0-point vibrational motion in molecules, so it's something you can never escape, even in absolute zero. And so these kind of processes of how atoms move are fundamental in anything to do with energy transfer. And so today I'll talk about magnetism, but of course, in a general sense, these are very important interactions for processes like photosynthesis. Okay, where you have local excitation of electronic energy levels, which then can somehow dissipate and transfer through electron transfer pathways to then do chemistry elsewhere and then store energy, and then therefore respiration goes on. So it's an incredibly important way of moving energy around. And in terms of something more, I guess, applied chemistry, we can talk about luminescence. So for instance, the phosphorescence, and we saw a bit of luminescence spectra in Kevin's talk just now, and these properties all rely on energy transfer, and these non-radiative energy transfer pathways are heavily reliant on vibrational coupling. And so there's a big interest in understanding how this works at a fundamental level. In terms of the theory, it's quite hard, and I'll give you a little bit of an insight into what we're doing for this, but if you were to try and tackle the full vibrational quantum problem at sort of an equal treatment of electronics and vibrations, you very, very quickly get to intractable problems. And so the fundamental approximations we make in computational and quantum chemistry is the so-called Born-Oppenheimer approximation, where we separate nuclear, the quantum mechanics of the nuclear wave functions from the electronic ones. By doing that, you've already cut your vibration electronic coupling problem and made lots of assumptions on the strength of that interaction. So there are really fundamental questions here about how you treat many-body quantum problems, and vibrations make this really difficult. Okay, so back to the sort of main focus of today's talk, though. In our group, we're interested in vibronic coupling or spin vibration coupling for lanthanide molecules. We have a big focus on, and we are interested in single molecule magnets. And in this domain, we think about vibrations as according to a loss of memory. And Kévin touched on this a little bit. And I'll give you a slide. I'm not going to go into too much detail for this audience on that. And of course, in qubits, we have vibrations which can lead to decoherence. Of course, there are many other decoherence pathways, but vibrations are one of them. And then going to, again, the applied end of things, you know, where we actually can sell molecular technologies because they're used nowadays in MRI contrast agents. The electronic spin relaxation time, T1E, is a crucially important factor when we're designing a contrast agent or using one, because this gives you information, or it affects your nuclear spin relaxation time, which is crucially important for medical diagnostics. Okay, so there's a lot of utility in studying magnetic molecules and how vibrations interact with them. Okay, so the first part of my talk, the first half will be on single molecule magnets, and the second half will be on sort of more generic vibronic spectroscopy. So single molecule magnets, again, I'm not going to labor this point too much, but we have a series of electronic energy levels that are separated by the magnetic anisotropy. And so in many cases, so in this talk, I'll be focusing on lanthanide single molecule magnets, where we have a total angular momentum ground state, which is comprised of both spin and orbital momenta. And so the MJ subscripts, or the projections of the total angular momentum, are the quantum states we're interested in. And these are separated here by the crystal field splitting, which induces the anisotropy in the magnetic anisotropy in these molecules. And so we like to think about this energy barrier to magnetic relaxation, where we have this easy access magnetic anisotropy, where we have a ground state with a very large projection of the magnetic moment that is doubly degenerate, and we can assign as an up and a down notation to these lowest energy doublet states. And this is where we like to store our classical information in a single molecule magnet. And the reason we can do this is because there are slow transitions going from, let's say, the 0 to the 1 state. Okay, and these occur. This is an exchange of energy. If you're going to move around, shuffle these energy through these different energy states, a molecule must absorb or emit energy to do so. Unless we're talking about quantum tunneling, but I'm not going to talk about that today. Okay, So vibrations in single molecule magnets, these, of course, if you take a crystal structure or you draw a picture on a piece of paper, as a chemist, you draw a molecule, you think about a molecule, often we just picture a static set of coordinates. But that's, of course, not real. That is an average or an equilibrium picture. In reality, as I mentioned, there are always vibrations occurring, even at absolute zero. And so these vibrations will modulate the electronic states, or the Hamiltonian, as a function of time. And so essentially you have periodic motions of the molecule, and this changes periodically your Hamiltonian. Therefore, it should change in technical terms your wave functions as a function of time. And so if you're taking, let's say, the average coordinates and you do an electronic structure calculation, you obtain the average, or the time average wave function. But of course, the instantaneous perturbations by distorting your atomic coordinates is how your vibrations lead to spin phonon or vibronic coupling. So in this talk, spin phonons and vibronic coupling, I'm going to use synonymously, because in reality, in any real experiment, we have a solid sample. Even if it's a solution phase, you still have, an extended material, right? And so in these cases of solids, we talk about phonons. These are quantized vibrations in the solid state. Crystalline or amorphous phase, because you still have phonons in amorphous phase as well, which is something we're starting to think about. Whereas in chemistry, we're usually talking about vibrational modes in the gas phase, so isolated molecules. And so these terms of spin phonon or vibronic coupling are more or less the same thing, but it does depend on context. Okay, so forgive me if I switch terms, I try to use them synonymously. So in single molecule magnets, we have these transitions, and these are enabled because you have a modulating Hamiltonian, electronic Hamiltonian. So this allows the transitions to happen. So essentially, a vibrational motion will couple this lower state here to this first excited state a little bit by how the Hamiltonian is changing as a function of time. And this is how we permit the transition to occur. And so these transitions we usually treat in perturbation theory, and I'll get to that in a little bit. And so for single molecule magnets at high temperatures, we talk about relaxation occurring over a barrier via the Orbach regime. And so at high temperature, these dynamics are dominated by spin phonon, single phonon interaction. So these are either single phonon absorptions, where the molecule is gaining energy and absorbing vibrational energy from the lattice, or emitting as we go down the other side. And this leads to this concatenated process of multiple single phonon absorptions and then emissions is what is known as the Orbach process. So a note of possible confusion for the students in the audience. This is often described, the Orbach process, as a multi-phonon process. And as a whole, that's true. But just to keep in your head that this is all occurring from single phonon absorptions and emissions. So it's a multi-phonon overall process that is actually underlyingly run by single phonon events. Okay, so there's not necessarily any correlation between phonons that occur that are being absorbed here and here or emitted over on the other side. Okay. And this leads to an exponential temperature dependence that is just like the Arrhenius law, which you will all well know. And at low temperatures, which is, I'll touch a little bit on towards the end, the middle of the talk, but I'm not going to focus on that today. We have two phonon processes where you really do have the concerted interaction of two phonon modes or two vibrational modes simultaneously to affect relaxation. And that happens at lower temperatures. Okay, so how are we trying to solve this problem? Now, there are, the literature is replete with examples of measurements of single molecule magnets and theoretical models for these things and how you can try and understand improvements or deficiencies in certain molecules. But we decided that it would be quite interesting and a tough problem to try and crack to simulate the relaxation dynamics of molecular magnets fully ab initio. And we're by no means the first group to do this. Frank Nace's group and Mikhail Atanasov have been working on this for some time as well as the group in Valencia, led by Alejandro Gaita Ariño and also with Eugenio Coronado, and also the San Vito and Alessandro Lunghi in Dublin have been looking at these kind of problems at magnetic molecules as well. And the general approach, and all of these groups take subtly different flavors to this, but we usually start by taking a computational approach to optimizing molecular geometry, whether that's in a crystalline phase or a gas phase, and calculating vibrational modes. And that's usually done with density functional theory. And so here is a first step where we are making already the assumption that we have a weak coupling between vibrations and electronic degrees of freedom, because we are saying inherently by using a density functional theory method here that we are using the Born-Oppenheimer approximation. Now, you don't have to, but that is the most common implementation. So we now play in our calculations here, then I'll talk about we are using gas phase optimization. So there is another layer of approximation, right? We are not treating the full solid state structure in the crystalline or even the amorphous phase at this point. So we calculate vibrational modes, okay? So this should be hopefully a comfortable thing. And then we then seek to understand how each vibrational mode will modulate the electronic Hamiltonian, which is in essence calculating the spin phonon or the vibronic coupling. And we do this by quite literally taking every vibrational mode of the molecule and distorting the molecular structure along the normal mode coordinates. So if there's a CH oscillation, we are distorting the CH bond and then recalculating the electronic structure every time. And we do this with CAS-SCF calculations with spin orbit coupling. And so this allows us to construct the electronic structure how it's modulated by each vibrational motion. From that, we can then use first order time-dependent perturbation theory, which essentially leads to Fermi's golden rule for a single phonon process at first order, to give us this equation here, which is telling us the rate or the transition rate between any two states, I and F, and that's proportional to a sum over vibrational modes J. And this element here is the matrix element of how the two states are mixed by a vibrational mode. So this is an off-diagonal matrix element, essentially induced by a vibrational motion. Then we have this part here, which is essentially the statistical occupation of that vibrational mode. And in the solid state, we would talk about Bose-Einstein statistics, but in the gas phase, it's equivalent to talk about Boltzmann population of a harmonic oscillator. So they're the same, they are related. There are subtle differences at very low temperatures there. We have conservation of energy, of course. The difference in electronic energy states must be made up by the energy of the vibrational mode. And then we have a line shape function. Okay, and this latter part is required especially from our gas phase calculations, because in a gas phase vibrational calculation, you have discrete vibrational energy levels. Now, if these, because of the delta function here, if those vibrational energies do not exactly match the electronic energy gap, you have no transition. Now, that's not true in reality, because in reality, we have dispersion of the vibrational modes, we have finite lifetimes, lots of effects that happen, and then we have these broad vibrational peaks. So we add a broadening here that talks about dispersion and those other effects. And then once we have all of these relaxation rates, this sets up a matrix of however many states you have squared. And this tells you all the transitions between them. And then you can solve this master equation. This is a classical Markov, so probabilistic type rate equation. And we simply solve this by, it's a diagonalization of another matrix here. And then we get out of this the relaxation rates between all of the states. And so we've been studying, in particular recently, these dysprosocenium single molecule magnets. So this work actually started when we published this Nature paper a few years ago. We started doing this project. It's taken a very long time to finish because we've come across lots of interesting questions and problems along the way and had lots of things to iron out. But by the time we got to there, the Jeff Long and Ben Harvey groups from California and had added a few more examples of dysprosocenium single molecule magnets, as had Richard Layfield's group in Sussex. And so we have a family of these materials which have very similar and yet in some senses quite different relaxation properties. So on the right-hand side, we have the relaxation rates experimentally as a function of temperature. And the compounds here are ordered 1, 2, 3, 4, 5, 6 based on their 100 seconds so-called blocking temperature, which is just a convenient way of defining some benchmark. And so we find that 1 has the fastest relaxation rate, so it's quite a lot faster at low temperatures than the others. And then 2 to 6 are much closer together than 1 is, but still there is some splitting of these systems. And at the higher temperature end, where we're talking about the Orbach relaxation, there is a dispersion between these systems. So 1 is always the fastest, and 6 is always the slowest. And in fact, 2 to 5 are very, very close. And if you take into account the uncertainties of relaxation rates from a distribution model of their relaxation times, actually 2 to 5 cannot be distinguished in this regime. They're actually within error the same. But 1 and 6 are distinctly different. And so the question we asked is, why are they different? And can we understand something about the structure that leads to these spin relaxation differences, and therefore try and design new features in single molecule magnets? And so we've performed the approach that I've just mentioned, just outlined to you, which is an ab initio relaxation calculation for all these 6 compounds. And you can see the results here. So the black dots are the experimental Auerbach relaxation rates, and the colored lines are different simulations. The solid lines include no calibration of the gas phase vibrational modes to the experimental ones, whereas the dotted lines include a calibration factor. So there's a very small change here. And the different colors indicate, so the different numbers here relate to different line widths. So this is the line shape function that we're adding on the end. And keep in mind from the experimental spectrum, we have something on the order of 6 to 20 wave numbers. And so these are sort of the realistic ranges. And again, you can see there's a little bit of change, but not a huge overall shift characteristically of these things. And so we're quite confident that our method is robust in terms of providing realistic approximations. But what we can note is that's very clear is that we overestimate the absolute relaxation rates by about an order of magnitude. And that's consistent across these 4 compounds. And indeed, across our other work on other materials as well, this seems to be a consistent feature. And to head off the question from Elisa, if you're still there, because you've asked me this before, why do we see this? We don't know. We still don't know why we see this overestimation. There are so many approximations we make in this method. It could be any one of them. And we are sort of systematically working our way through to try and understand why, but we don't have an answer as yet. So while we do overestimate things by a factor of 10, okay, you could say that's terrible. But if you think about it in terms of a computational, completely ab initio approach, that's not bad as far as I would be concerned, because consider that your rates are changing by many orders of magnitude as a function of temperature, and we're only off by sort of 1. So it's a sort of small shift on the scale of things. But the most important thing for me is that we get the experimental ordering right. We always find in this range of line widths that compound 1 is the fastest and 6 is the slowest, and that 2 to 5 are very similar to each other. And so this tells us that whilst we're overestimating absolutely, the relative quantitative rates are accurate for our compounds, and that is we are discriminating the differences between them accurately with ab initio calculations. And so to me, that's a really nice thing, okay, which means we can believe these results in some way and try and understand what they're telling us in terms of the chemistry. And so then the question comes, okay, how do you pick apart the differences in your different chemical systems? Now, the trouble with these compounds is that you have the overall relaxation rates that I've just showed you are the eigenvalues. They are the slowest non-zero eigenvalue of a 16 by 16 matrix. And when you diagonalize a matrix, we do this numerically in a computer because there is no analytical solution for a 16 by 16 problem. Okay, yes, you can do it by hand by doing many different determinants and blocking them all out, but that doesn't lead you to an analytical answer. And so there's no way to separate the contributions of different states or different electronic transitions or different vibrational modes. And so you just get this answer. And so we've played lots of different games over the years about trying to understand these rate matrices and extract some information. And basically until now, I think everything we've done, so that includes the Nature paper, that includes a JAX paper, that includes a Chem paper, I think they were all the wrong way of analyzing this matrix because it's an oversimplification. Whatever we did in the past, I don't think was right. So hopefully I can explain to you what we are thinking now. So the key point to think about here is that because we have this delta function, if I go back to the expression, this delta function tells us that only vibrational modes that are very close in energy to electronic states will cause a relaxation step, okay? And so that means that we must have only very few vibrational modes that contribute to any single transition. So actually on average, it's only about anywhere between say 2 and 3 or at most, right? Often it's just 1 that dominates. And so each transition, you can actually simplify this matrix quite a lot. And so what we decided to do was think about the mode averaged contributions to the relaxation matrix. And so here we're defining a set of new matrices. So these are each element, so the F5 element, so there are 16 by 16 elements of each of these terms. Okay, so these are the different matrices. And each one is the sum over the 3n minus 6 vibrational modes of the gas phase. And what we do is we just take each of these individual terms. So we have the spin phonon coupling part, so that's the electronic matrix element. Then we have the density of states part, which relates to the line width function and how close in energy you are. We have the statistical occupation part, and we take each of these elements and we weight them by how much is the jth vibrational mode contributing to the total sum of over all vibrational modes. And so we're essentially averaging these parts of that rate expression. And by doing that for the spin phonon density of states and occupational term, we can then compare this product of for any single matrix element to the total rate to then obtain an effective number of modes. So what is the multiplicative factor? Once you've averaged those quantities over all of your modes, what is the effective number of modes you have that are giving you the actual total ab initio relaxation rate for that element? And so once you do that, you have these matrices which define these four components. And so you can reconstruct or decompose, whichever way you want to call it, the total 16 by 16 rate matrix here into these four different matrices. And so this circle here indicates the Hadamard or the element-wise matrix products. Okay, so each element here is just of this matrix is just the product of the elements of each of these matrices at the same point. And so you can now think about having these individual parts for any molecule so that you can chop and change between different parts of different molecules. So for instance, I could say, okay, let's take the spin phonon coupling from the original dysprosocenium, but pair it up with the average number of modes for each transition from Jeff Long's, one of Jeff Long's molecules. Or I could take the density of state, so how close are your energy levels from Layfield's molecule, and put them with one of Jeff Long's, or whatever you want, and see how that changes the rates. So comparatively, you can start to think about how you are switching out different parts and changing the dynamics, and therefore making comparisons between what's important. Okay, so this is a bit of an imposing table, but I hope to break it down for you. So the top part here, we are starting with a calculation of the relaxation rates for compound 1. This is the fastest dysprosocenium single molecule magnet, and that is one of from the Jeff Long, Ben Harvey chemical science paper. Okay, and so this row here says when we have all of the parts from just that molecule, we get its relative rate to itself being 1. Okay, and this is the absolute numbers here. Now, if we swap out the occupational factor, so that is the temperature dependence of the modes, for that of Layfield's dysprosocenium molecular magnet, so that is the slowest, compound 6, then we can reduce the relaxation rates by a factor of 10. Okay, whereas if we do all of the other single swap outs, so that is we change the spin phonon coupling, we get a barely noticeable change. If we change the average number of modes, again, it's not an order of magnitude like this one is. And then finally here, we could change this density of states part. And again, it's a bit of a change. It makes it twice as fast, but it's not an order of magnitude. This is a factor of 10, right? And then we could do the reverse. So we can take the matrices just from compound 6, the Layfield compound, and then swap out those parts individually. And what we find again is sort of the reverse, that when we swap out the occupation term here, Q, for compound 1, we get a factor of 10 increase. So this way it got 10 times slower, but then doing it the other way around, so replacing it the other way, you get 10 times faster. And so these are not exactly the same numbers, because remember, these rates correspond to the second, so the smallest non-zero eigenvalue of a 16 by 16 matrix. And it's not trivial when all of these things are taken as products together, what that comes out as. But you can clearly see here that they are the same order of magnitude change, which tells us the same thing, that this occupational term is the discriminant between the worst dysprosocenium single molecule magnet and the best dysprosocenium single molecule magnet. So it's simply the occupation of the vibrational states. So what does that mean? Let's have a look at this term a little bit more closely. So remember, this occupation term is telling us about how the excited vibrational levels of some mode J are occupied at some given temperature. Okay, but recall that because of the delta function so I'll go back again to that equation just to refresh your memories. Because of this delta function, the actual energy we are using for any relaxation step must be equal to the difference in electronic energies. That is how we define h bar omega being the vibrational energy in this expression. And it is this term here that tells you how close is this chosen h bar omega to your actual vibrational mode, J. Okay. So we're always using the energy gaps of our vibrational mode, which are the same as the electronic energy states. And so when we find that this Q term is dominant, that tells us that it's because the energy gaps are larger. That is, by using the occupation term from the Layfield molecule, it slows down relaxation because the occupation of the higher energy vibrational states is lower than in the worst dysprosium single molecule magnet. And that occurs because the energy spacings of the crystal field states are bigger in Layfield's compound than they are in the worst dysprosium single molecule magnet. Okay, and so it seems like a trivial result after all that effort that it's the crystal field splitting, make a bigger, more anisotropic single molecule magnet and you make it better. But that is the result of this analysis. And by doing the exact same analysis, comparing the original Nature paper dysprosium molecule to Layfield's science paper, we see more or less the same thing. There's a little bit of an influence of the spin phonon coupling being, playing a role. It's not as clear cut as this one, but again, it's dominated by the crystal field splitting. Now, I point that out with great importance because we said almost the opposite thing in the conclusion of the Nature paper, that it was these specific CH vibrational modes that were so important, and you've got to per substitute all of your carbon positions on the ring to get rid of those CH modes to make relaxation slower. And then lo and behold, that's what Layfield did, and then he made it much better. But that's not actually why it changed. It's because if you look at the coordination geometry, it is more linear, it is less bent, and the rings are slightly closer. You get a larger crystal field splitting. It is coming down to the simple answer is the right one at the end of the day. It wasn't really due to the spin phonon coupling. So that's in some senses an interesting result for me because it sort of contradicted my original thoughts about that whole project. Which is nice because now we can have a method of actually robustly understanding how to separate the different parts of these molecules and compare them from an ab initio perspective. And building them on top of a predictive or relative quantitatively accurate simulation, we can now have some faith in what we're doing. Okay, so on that last point, because we have this relative accuracy and we trust these rates, we now have a tool that we can use to predict new compounds because we trust the relative rates. So the rates I'm going to present for these made up molecules are not necessarily the true absolute rates. We're not saying you would get these rates because we don't match the experimental ones of the real compounds. But relatively, if we find something that is much slower than the existing compounds, we can think that those molecules will be much better single molecule magnets. And so that's what we've done here. All of these colored lines correspond to different choices of putative new single molecule magnets. Some are not our proposal. So for instance, this blue one here at the top was proposed by the Valencia group. This orange one here was proposed in a really nice inorganic only single molecule magnet paper where they used a bunch of, I think they were all homoatomic 5-membered rings, sandwich complexes to propose new single molecule magnets. And indeed, they thought this one was quite good. But it turns out to be not so good from our methods. And then we have a bunch of substituted and sort of not substituted cyclopentadienyl and also cyclobutadienol compounds. We did a bunch more, but this seemed sufficient to illustrate the point. Some are predicted to be worse than the black one here, which is compound 6, which is Layfield's science paper. But noticeably, 2 of them are predicted to be far, far better, orders of magnitude better. And they are, perhaps unsurprisingly, the bare cyclobutadienyl anion, and I'll talk about that in a second, and then also the CP star or C5 methyl 5 cyclopentadienyl molecule. Now, of course, this gray one people have been trying to make for years, years and years and years. It's very, very hard to isolate because there's such a small ligand there that you will always get something coordinating, and that destroys your properties very, very quickly. But we're showing here that if someone can find a way of doing this, it is going to be a very, very interesting molecule to study. Now, there are going to be lots of caveats because this is all done in the gas phase. And so how you isolate this thing in a matrix in some way has to be very protected. So, Kévin mentioned SMMs in MOFs. Here's a challenge to you all, and try and get this in a MOF. That might be a nice way of protecting it from coordinating small molecules. Who knows? So there are some nice synthetic challenges here. But of course, you know, cyclobutadienyl is an obvious target because you now have a C4 ring, which is a 2- dianion as an aromatic anion. And so you have a much higher charge that you're putting close to your dysprosium, so the crystal field should be much bigger. In actual fact, this doesn't have a crystal field splitting that's any bigger than Layfield's molecule, and neither does this one. Actually, they're both very, very similar. So it isn't actually the crystal field splitting for these latter two, which gives you the different properties. It turns out to be vibrational modes. And so they both turn out to be better than the Layfield molecule because all the vibrational modes happen to be off resonance with the electronic states. Now, that's something that's very hard to predict. You certainly can't just write a molecule down on paper and say, oh, it's going to have that property, but you can calculate it. And so these plots show us here the transitions from the ground to any pair of excited states, these orange lines, and these green lines are the low energy transitions between different excited, different doublets. And so you can see for almost all of them, they are not resonant with the calculated vibrational energies, which are these blue sticks. And so that just happens by circumstance. And so what you find is that the barriers aren't actually any bigger for these two. In fact, you can see the slope of this gray one is considerably less than the black one. So the barrier isn't any bigger. But essentially the prefactor in your Orbach term, the tau naught, which comes from all your vibrational stuff thrown into this constant, is orders of magnitude slower. And so you get far, far slower relaxation. So that's a really quite, I mean, it's an obvious point to make that you can tune vibrational modes to improve single molecule magnets, but the point is we now have a quantitative predictive method to do so. And so if you have ideas, I would be very happy to run this through this procedure and tell you if it's worth making or not. Now, I haven't turned this into a website where you can just upload an XYZ file and it will give you a rate. That's an idea. Maybe I should try and apply for funding. I don't think anyone will pay me for that, so there's no point patenting it. But if it comes to that, I'll get in touch. Kevin, you seem to know the ropes. So anyway, I think that's a really nice sort of, not a conclusion to this piece of work, because of course, there are many things you can think about designing new molecules. And indeed, Alessandro Lunghi's just got himself an ERC starting grant to use machine learning to try and predict some new, molecules and structures, because of course, the solid state is very important. To have certain spin dynamic properties. And I think that's the way forward really for doing this, because by hand in chemistry, as soon as you make a molecule, then you put it in a crystal structure or an environment, and it's different from the gas phase. And so this specific approach only has limited relevance to reality, but I think it's a very useful step in the right direction. Okay, so a very quick point on the 2-phonon stuff. So this is the original dysprosocenium cation from the Nature paper, and we found, of course, at low temperatures, this change in relaxation rate, abrupt change from the Orbach regime. And this is the Raman, the 2-phonon Raman term. This has a power law temperature dependence. And this is a true 2-phonon process. And so here I'm just drawing a sketch that I like to give my undergraduates for how this process works, because you don't draw arrows directly between states anymore, because this transition is a simultaneous absorption and an emission process of 2 different phonons. And it is not, you never transit via a real excited state. So drawing these arrows going to any real state here is not true. And so this here is the expression, or one of the expressions for the relaxation rate in a 2-phonon process. Of course, it's far more complicated now. You have 2 phonons, I and J, you have 2 occupations, you have 2 density of states, you have a different delta function here. So conservation of energy is now the difference in the energy of these vibrational modes must match the difference in the energies of I and F. And then you have to integrate over all possible vibrational energies, which makes this far more complicated. And there are lots of subtleties in how you do this in practice. But anyway, the point is you sum over all intermediate states C. So anything that's not I and F, you are trying to see how the vibrational modes mix states I, the initial one, and the final one, F, via a state C through spin-phonon coupling. So this is second-order time-dependent perturbation theory using first-order spin-phonon coupling. So the first-order spin-phonon coupling is these matrix elements here, so that hasn't changed from before, but we are now doing the second-order in time-dependent perturbation theory. And so we never transit via real state, and the contribution is via all excited states C. So I like drawing it like this, and this is the meaning of a virtual state. It's never populated in this transition. It's just perturbation theory. Okay, so calculating this is a heck of a lot harder, And of course, you need an environment, because we are now talking about very, very low temperatures, which means low energies, which means low energy vibrational modes. And so the gas phase has these discrete high energy vibrations, and that's more or less irrelevant. And we can therefore calculate Orbach fine with that, but we cannot get the Raman. Okay, so we need an environment, and we can do this in the crystal structure. We're working on it now. That's a really hard problem. Went away and did these sort of QMMM calculations, where you have a layer of solvent described by real density functional theory, so molecules and basis sets and things, and then a semi-empirical or molecular mechanics model on the outside, where you have a bunch more DCM. And so a lot more effort computationally to find the vibrational modes of this thing, this chunk. And so we have about 3,800 vibrational modes for this particular problem. This is a picture of what it looks like from the inside. You have a molecule inside lots of solvent, and we're calculating all the possible vibrational modes of this. So you can imagine that this really sucks as a computational chemist to try and optimize the geometry of this thing. And the meaning of that is also a bit questionable, but we can talk about that if you have questions. This is all preliminary, of course. We haven't actually finalized all of this, so this is just bleeding edge. But now this is the density of states we have for this sort of amorphous solution phase situation. And so instead of just having these discrete peaks, and so these big peaks correspond to the dichloromethane energy stretching, these little peaks are the single molecule magnet in the middle, and then this big lump at the bottom is all the pseudoacoustic modes of the lattice. That is, little motions of molecules moving between each other, or slight rotations. And of course, these will project, if you do the analysis, onto vibrational modes of solvent and molecule. But in general, these are the very low energy modes that are going to contribute to the Raman regime. And if you do it and you throw it all into the computer, and you get the Orbach and you get the Raman from this picture, you get a really, really nice simulation of the experiment. So orange is a calculation, fully ab initio. There's no fitting parameters there. We have still this constant line width, which I've just fixed at 10, which is sort of in the middle of the range we find experimentally. And then this blue line is the experiment. So I'm really, really excited about pushing this further and actually getting completely ab initio, no parameter relaxation rates across the entire range of timescales. Error bars on these calculations are from a few different solvent bowls, because of course the stochastic choice you make is going to influence your results, but it's not huge compared to the changes on these data scales. So there are lots of things we have to iron out for this and so on, but I just wanted to say we're moving in the right direction. We're almost there for this. Okay, so now I want to move to the second part of the talk, which hopefully I've got enough time to get through, but I'll try not to skip too quickly. We've been looking at this ytterbium trend cell complex, which is very boring in many respects, because it's incredibly well studied for a long time now. It has very well defined spectroscopy, so we know where the crystal field splittings are. We have good EPR. We know that it's a lovely molecule. It's neutral. It's air stable. It's got C3 symmetry in the solid state, and it's easy to make, and so many things. So it has a lot of nice things going for it on the chemistry side. It also has a very well studied electronic structure and magnetic properties. It is most certainly not a single molecule magnet. This is the really nice image from I think I can't remember if it's the Inorg Chem or the JAX. No, it must be this Inorg Chem from Casper's work, where you have luminescence that tells you that the first excited state is at 470 odd wave numbers, but yet if you assume you have this Orbach thing where you draw a linear slope on an Arrhenius curve, like everyone was doing for a decade for lanthanide single molecule magnets, you get a barrier that's just absolutely ridiculous and makes no sense, because it's nothing to do with Orbach relaxation. So you plot it on a different scale, this log-logs plot, and you see it's linear, which means you have this power law regime. And so this is really just all Raman two-photon dynamics at low temperatures. So there's no Orbach SMM behavior in this thing. Okay, but it's also been studied for its coherence properties, and diluted in the solid state, this is a really, really nice qubit. And so these are different Rabi oscillation experiments on different nuclear spins, so different hyperfine transitions. These should be MI, I think, not I. Different hyperfine transitions of this material. So in the lowest lying Kramers doublet, you can have many different hyperfine states from the naturally abundant nucleus of ytterbium, and you can transfer between these different hyperfine states and perform coherent manipulations. And so these oscillations are proof that you can do coherent quantum manipulations of this material. Okay, so this is an ytterbium-3 compound, which is 4F13. So we have, one hole, let's say, in the electronic structure. So it's a doublet F term for that configuration, which is split by spin orbit coupling into the 7 halves and 5 halves total angular momentum states, which are further split by the crystal field interaction into Kramer's doublets, because this is an odd number of unpaired electrons. Luminescence spectroscopy, this is old data from the Chem paper that we've replotted, tells us where the energies of those states are. So this is a luminescence spectrum that's been flipped and reversed to look like an absorption spectrum, just for clarity. So this is your essentially your zero phonon line, your 0th state. So that's our ground state. And then at about 470 wave numbers, we have the first excited crystal field state here. And then 3 and 4 are our second and third excited doublets again. And we have all these subtle features here, and this inset shows this low energy regime. All these subtle features, which at the time they didn't really know. They said they were vibrational sidebands, but there's no more assignment. And so this is where this experiment or this study started, is trying to understand what these were. And so all that was done by the Copenhagen group with Celios and co. And they teamed up with Steve Hill, who you'll hear from in a couple of weeks' time, to look at the far infrared magnetospectroscopy, or FIRMS, data of this material. And so this is simply taking an infrared spectrum at 0 magnetic field and then applying a variable magnetic field to see how the FTIR changes. And so you can see here the 2 different spectra at the smallest and largest field, so 16 Tesla, are pretty damn similar. There's not much differing between them, but little shoulders of change and little shifts happen, okay? Which mean there's something is changing. So if you then divide, so calculate the average spectrum across all fields, and then divide each field spectrum by the average, you get this picture here. And so this is just a few different field steps, but you can see that there are features that are changing as a function of field. So anything that appears here as a squiggle means it is changing as a function of field. Okay, so there's something around 450 plus or minus 100 wave numbers, and then something around 770 or something like that. You can also plot these data as a heat map, and so it starts to look like this. So now your brain switches on to saying, hey, this looks a lot like Zeeman splitting, and that's exactly what we're trying to probe here. And you can zoom into this most feature-rich region around 450 wave numbers, which I do here, to show these really nice curves. And so these are states that are dependent on the magnetic field, and their energy is changing. And we are measuring that with an infrared spectrum. And so this is a FIRMS spectrum that we're going to try and understand. Because of course, anything here that's changing as a function of field must be somehow related to an electronic state, because vibrational states should not have on their own a field dependence. So anything that has a field dependence must have some part of an electronic transition happening. So this is our attempt to measure the vibronic coupling in this material. Okay, so if we think about what you can have in a firm spectrum, you can have a purely vibrational transition. And this is an electric dipole where you are changing, you're distorting the geometry of the molecule, you're changing the electronic density, and therefore you have a dipole allowed transition. Now, this shouldn't have any field dependence, and there are lots of these. So this is the raw transmission spectrum. You have lots and lots of absorptions here, which means that you have lots of vibrational modes. Duh, it's a molecule, right? And we're doing an IR spectrum. There are lots of vibrations. But we don't see all of these, of course, in the spectrum, because most of them are not coupled to electronic states, or not so important, let's say. And that's the initial assumption. So let's start with that. So you shouldn't see those. Then we, of course, have the purely electronic transitions, that is going between the different Kramer's doublets of the crystal field split states. And these would be magnetic dipole allowed transitions. Now, magnetic dipole allowed transitions are much weaker than electric dipole transitions, which is a well-established fact, which is why you need resonant cavities in EPR, and you can't just do free space EPR. I mean, you can do free space EPR, and people do at very high powers, high frequencies. But essentially, magnetic dipole transitions are far, far weaker than electric dipole ones. Okay, and so we should see these, but there are only few of those, because we only have 4 Kramer's doublets. And so we're only going to have a certain number of transitions in these energy ranges. And these are, we know these from the luminescence spectrums. We know where these occur, and that's where these blue lines are. And then finally, we should have vibronic transitions. And these are going to occur at many different places and have a field dependence. And so just a quick interlude here. vibronic transitions, you'll know from Frank Condon principle, where you have an absorption and you go a vertical transition, you go straight up and you don't change nuclear coordinates, and then you have some vibrational relaxation and then emission if you're going to be, fluorescence. And this is the Stokes shift. But we don't have that in this case because we're doing 4F transitions, which means that the geometry is not really altered by making the electronic transition because the electrons are non-bonding. And so we assume that the changes in geometry are negligible and that the vibrations of the ground and excited states are all the same. Okay. So if we now think about the possible Fermi's transitions we have in our picture and build a small model, we can think about just a simple 2 Kramer's doublet picture. So we have a ground Kramer's doublet down here and then an excited Kramer's doublet up here. And these both have a 0th vibrational state, so no vibrational quanta, and then a 1 vibrational state where we've added a vibrational excitation. Okay, so that's why these are doubled. So this is our ground crystal field state with an extra vibration, with a vibration, and this is our excited crystal field state with a vibration. And so the purely electronic lines are these blue ones, and the EPR transition is also a purely electronic one that I show here, but we're far too high energy to see that. That's of course in the microwave regime, not IR. Black ones could be vibronic, and that would be an inter Kramer's doublet vibronic transition where we're going from the 0th vibrational state up to the 1st vibrational state, as well as changing an electronic quantum. These red ones are hot transitions because we start from an excited vibrational state and go to a vibrational de-excited state. These green ones are the pure vibration. So we're not changing electronic state. We're just going 1- to 1-, but we're changing the vibrational quantum from 0 to 1. So that's purely vibrational. And then these black dotted ones here are the intra Kramer's doublet vibronic transition. So we're going from the -1 to the +1. So we're doing an EPR transition associated with also a vibrational excitation. So these black ones are the vibronic ones that we're interested in. Now, we know, of course, the 0 field, no vibrations, ground to first excited Kramer's doublet from luminescence. That's 470 wave numbers. That's that blue line. So anything below that must be these intra Kramer's doublet ones, because we're not able to do these inter Kramer's doublet vibronic transitions, because that would have to be over the electronic energy. It would be the first electronic excitation plus a vibration. So that's on the right-hand side of this blue line. So anything on the left must be these intra Kramer's doublet vibronic transitions. It can, of course, also be a hot transition, but these spectrum are at 4 Kelvin and they trail off incredibly quickly due to population of this excited vibrational state. So it's mainly dominated by these intra transitions. So on the left of those, we must have intra Kramer's doublet. On the right, of course, we could have inter Kramer's doublet, intra Kramer's doublet, and any kind of thing. Okay, but on the left, we must have intra. And so the question really becomes, if we can have intra Kramer's doublet transitions, that is a tiny EPR electronic transition, but then any vibrational mode on top of that, why aren't we seeing vibronic intra Kramer's doublet transitions all over this region? 150 wave numbers. If you go back to the raw spectrum, we have a heck of a lot of vibrational modes in this region. Why are they not observed in this spectrum? And I'm running short of time, so I'll just move quickly through this. But basically, if you use perturbation theory, you can show that the intensity of a Fermi's spectrum gives you this divergence in intensity in first order perturbation theory when you have vibrational modes that are close in energy to your first excited state. Now, I'm not saying that you are absorbing that vibrational mode. Remember, these are not absorptions of phonons or vibrations to make the excitation. We're driving a combined electronic and vibrational excitation with an optical photon. So we're not absorbing a quantum of vibration to make an electronic transition, but we're driving both an electronic and vibrational excitation via a photon. Okay, and so when that extra vibration matches an electronic transition in your Hamiltonian, you get this increase in intensity. And so that's why we have this sort of envelope effect where you see these lots of transitions near your electronic doublets. But it doesn't mean that the coupling or the vibronic coupling of your other transitions are weaker than these ones. Okay, and that's a really sort of subtle point that's quite interesting, that's quite important. And so we've done more or less exactly the same thing as I talked about before to calculate the vibronic coupling. Optimize geometry, calculate vibrational modes. Then we distort the molecules, and here I'm just showing you how the crystal field parameters of the ytterbium are changing as you're distorting along a particular vibrational mode. And so again, we use CAS-SCF. We've done a few more special things here, but that's a detail. And then we can define a coupling Hamiltonian, which is based on the derivative of how the crystal field parameters change. And there are many ways you can define this. This is a pretty standard definition, which is the first order linear spin phonon coupling. And then we can calculate a firm spectrum by building this total Hamiltonian. So now we have the crystal field splitting of our electronic states, the Zeeman term, that's how the electronic states split in the magnetic field. And then we can construct a Hamiltonian here, which accounts for the sort of zero field standard harmonic oscillator of each vibrational mode, and also then how each mode is coupling to the set of electronic states via this expression here, this Hamiltonian. Now we don't perform this full sum because this basis gets huge. For every vibrational mode you want to include, even if you only include the ground and first excited vibrational state, you're doubling the size of your basis. Okay, so it's you're adding a power every time, so it scales exponentially and it's horrible. So we only can include, I think, a maximum of like 11 vibrational modes simultaneously before this gets crazy. But luckily, that's almost just enough to do the entire spectrum that we observe. And so on the top is your experimental spectrum in this most feature-rich region, and then on the bottom here is a ab initio calculation. So there's no fitting parameters at all between these two spectra. The only thing we've done is shifted the equilibrium electronic excitation from CAS-SCF to what we observe in experiment, because CAS-SCF without dynamic correlation gets it wrong by about, I think it's 60 or something wave numbers. So we just shift that electronic energy, but that's all we've done, right? So all the vibrational coupling stuff and all the vibrational energies are all ab initio. And all that really does is, instead of having the excitation here, we find it over here somewhere, and so we just shift it back down. And so we find this nice agreement, where these two pairs of modes are split in roughly the right amount and have the right sort of shape. We have this feature C here, which comes from another set of vibrational modes. This sort of more diffuse larger region D here is sort of represented by this. This higher intensity band is also represented over here, F. So we have some really nice features. And now what that means is we can break the calculation down into the different vibrational states and understand what the spectrum's telling us. So I'll go through this quickly because this is just wobbling molecular pictures, but we have a bunch of different modes of different symmetries in C3 symmetry that correspond to these different vibrational transitions. So these are remember, at this low energy below 470, we are must be doing an intra-Kramers doublet transition. So it's an EPR electronic transition and a big vibrational energy that's more or less the number you see here. So these are high energy vibrations at about 400 wave numbers. So they're higher vibrational numbers. And again, we're still below the electronic absorption, so we must be still doing intra-Kramers transitions. These get complicated because they're very close to the electronic excitation, but we believe these are dominated by intra-Kramers excitations. And then once we get past the first electronic excitation, we now see this inter-Kramers excitation. So now we've got a 470 wave number excitation of the electronic energy plus, I think this is, well, what's that? 50 odd wave numbers for these vibrational modes. So these are lower energy vibrational modes coupled to a higher energy electronic transition again. And so that's the spectrum. And so again, we have a nice representation, or a nice reproduction of the experimental spectrum, which gives us faith in trusting our results here. But we've shown, because of the envelope effect, the intensity of the firm spectrum does not directly relate to vibronic coupling strength. And so that's a really important point, that you can measure a firm spectrum and say, hey, look, we have vibronic features and it's the only strongly coupled states are around the electronic state. But that's not true. And so if you look at the ab initio calculated spin phonon coupling or vibronic strength, which we give this number Sj, you can see that across the entire energy range, there's strong coupling everywhere. And it's this set of modes here I've highlighted in black that are the ones we observe in experiment. So they're not even the most strongly coupled. For instance, this is much higher. And there are ones that are equal at much lower energy that we just don't see because of the envelope effect. And so now if we look at these low energy ones, we see these are perturbations of this, first coordination sphere, as you would expect. And again, these higher energy ones are much higher energy because these are deformations of these C5 rings, these phenoxy rings. So they're very high energy, but of course they are distorting very strongly this oxygen. And so that's a very, very strong contribution to the spin phonon coupling. Okay, and so overall for this molecule, so you can see the different symmetries mapped out here, we find that the doubly degenerate E symmetry modes are more or less always, on average, higher intensity or higher coupling strength than the asymmetry modes. So that's the first thing. And the second is that the modes that couple most strongly, so if you take a subset of these highest coupling strength modes, it's always occurring when the coordination sphere is being distorted by the first coordination sphere is being distorted. So again, that's not really an amazing, new conclusion. Everyone's been saying that for a very long time, but we can prove it. And we can show it from ab initio calculations and how it matches with the experiment. So that's really nice. Okay, so sorry for running a bit late and having to run through that pretty quickly. So what we've been working on lately is ab initio spin dynamics and calculation of vibronic spectra and the vibronic coupling, and we can show that they match in both cases very well with the experiment. And so we really trust the methodology we're using now. It's not just one experiment, it's many different techniques, different compounds. So we're quite happy with this. And we can explain the differences now in the dysprosocenium family, which allows us to explain differences in different single molecule magnets, but also predict improved ones. We've shown that this kind of firm spectroscopy, which again is not a new technique at all, is subject to an envelope effect that I don't think has really been discussed before. We can go into the details of that. I'm fighting with referees at the moment, but that's neither here nor there. And for this particular molecule, ytterbium tensal, the vibronic coupling is strongest for E-symmetry modes that distort the first coordination sphere of this material. And so that now gives us a point to start thinking about modulating those modes. So of course, yes, first coordination sphere, that's a bit obvious, but changing the symmetry of this molecule, how is that going to affect the spin photon coupling? Or, changing the molecule in a symmetric way, is that going to affect the E-symmetry modes, but not the asymmetry modes? And you can think about different ways of moving the chemistry to play and answer these questions. So a big thanks to two of my group, Daniel and John, who've been really driving this vibronic coupling stuff for many, the last 4 or 5 years, who have been doing this work. And then our collaborators, so John Marby and Stephen Hill in the Mag Lab in the US for doing the experiments on that last sample, and Stegios in Copenhagen, who've been providing the samples and kept doing the optical spectroscopy on that material. Thank you for these people for funding. Of course, thank you very much for your attention. I'm sorry for running late again. And that's all I have to say. Kevin reminded me that I should give you a bit of a shout out for the ICMM. So a very quick 2 slides on this. We are hosting ICMM in Manchester this June. It was postponed from last year. We would really like to do an in-person conference, but I'm afraid the risk is just too high and we cannot afford to pay another set of deposits that we're not going to get back. So this is a lovely Manchester town hall with a statue of John Dalton in the middle of it, who is obviously at Manchester. And I'm sorry we can't welcome you this year, but hopefully in the future, you'll be very welcome to join us in Manchester and have a couple of pints. So it's free to everyone. There is 0 registration fees. There is a scam, I think, going around for some ICMMM or something in some place in Canada, asking for fees and things. That's not us. So don't pay any money. This is free. It'll be on Zoom in the summer. We have some really nice plenary lectures. So my old boss and mentor, Keith Murray, will give the Olivier Kahn lecture this year. And we have a really nice array of speakers on different areas of molecular magnetism, but also, of course, things that are tangentially related. So molecular machines from our very own Dave Lee in Manchester. So the abstract deadline is approaching in the next couple of weeks. So please do submit your abstracts. There are slots available for oral presentations, and we will have poster sessions as well. I know Zoom isn't perfect, but it would be very nice to speak to many more of you more frequently. So please do come in and keep us company. There's the website here, which has all the links to registration, which is via Eventbrite, and then the abstract, there's a link there to submit them as well. So thank you very much for your attention. I'm happy to take any questions.
Yeah. Thank you, Nick, for this great and inspiring talk. Is there any question in the audience? Do not hesitate. Is there by Talal to start?
Yes, Nick, very nice talk. There are a lot of things. I have just something I did not get very well. When we were talking about intra-KD transition in the ytterbium tensal. Okay, you have a scheme, yes, very nice scheme. The black arrows, but I mean, what is the energy that you observe them in the spectrum, in the experimental spectrum? I mean, this would be expected to be very low energy.
Which black arrows? The solid black arrow?
The intra KD.
Oh, no, they're not low energy, because remember, your electronic part, yeah, that's tiny. That's, you know, fractions of a wave number. This is the Zeeman splitting, just like an EPR transition. So the electronic contribution is tiny, but you are also making a vibrational excitation. And remember, we have vibrational lines across the entire, you know, range of this spectrum, right? So you have vibrational modes at 100, 200, 300, 400, 500 wave numbers. And so if you do it at 500.5, right, that's the energy we're talking. So this is why I'm saying you can have, you should be able to see these features anywhere in the spectrum, because your electronic part is so small. But
so that's why you put it in the, okay, so the first part is KD1. This is what you call KD1, and then the four upper lines splitted by the magnetic field are KD2.
Correct.
Okay, so all right. Okay.
Yeah, so this bottom doublet here you see lowest, this is KD1 split by a magnetic field with no vibrational energy.
Yeah, and this is the zero phonon. Okay, the first one is the zero phonon one, and the one that is below at H bar omega is the first vibrational mode, let's say.
Well, H bar omega is the vibrational energy with one excitation, so one quantum of vibration. And so if you're changing from 1-, so that's the, you know, lower trending part of KD1 as a function of field, 1- with no vibrational quanta, so you're in the 0 point energy for some vibrational mode. And then you make only a vibrational excitation, so traditional vibrational spectroscopy. You don't change your electronic state, but you then excite a quantum of vibration. Yeah, so you go from a 0 to a 1. But if you do simultaneously excite a quantum, so you go from 0 to 1, but you now are going from the 1-, which is going downwards, to the 1+, which is going upwards. You are changing the electronic quantum as well as the vibrational quantum. So this is how we define the vibronic transition. So it's both vibrational and electronic. And this is where you now can introduce a field dependence to these lines, which can occur at much higher energies. The field dependence here is, of course, related to the Zeeman splitting of the KD1. There's nothing fancy about it. It's simply, you're observing essentially a vibrational mode that starts to look like it's got a Zeeman part, which is a bit weird. And that's why you see it in this infrared spectrum as a function of field.
And this can be at higher energy than the zero phonon. This is what, I mean, some of these modes are at higher energy than the zero phonon, which is than the zero phonon transition. Yeah. And this is because of the Zeeman splitting in this case. What I do not understand, why they appear at higher energy.
So higher energy than the electronic excitation.
Exactly, than the electronic excitation, sorry. Yes.
Oh, okay. So then that's just a different case. You're going from KD1, which is down here, up to KD2, which is up here, 470. That's your crystal field splitting. So now we're no longer doing EPR transitions, right? You would never see that as a, you know, terahertz transition, right? But you're doing this now, this really high energy electronic excitation, but also changing a vibrational quantum. Now, in this case, your blue line here is your pure electronic excitation, right? That's pure magnetic dipole, only electronic. And that would have a Zeeman spectrum. That would just be your pure sort of high energy EPR, high frequency EPR line.
Yeah,
right?
yeah, okay. Yeah.
Now, if you go beyond that, if you start saying, okay, I'm going to do that high energy EPR transition, but I'm also going to throw in a bit of vibrational motion. So I'm going to excite the electronic, but also a little bit of a vibration. Then you're going to be higher energy. And that's what you're doing. So you're now going to couple to lower energy vibrational modes. But of course, there's nothing to stop you, because there are vibrational modes across the spectrum that, you know, doing this low energy, this down here, this really low energy intra Kramer's doublet EPR, real EPR transition, plus just a vibrational mode that happens to be at 600 wave numbers. There's nothing to stop you doing that either. So beyond this point, it gets mixed, right? You get both things happening.
Thank you. Matej, question?
Can you hear me?
Yes.
Great. Thanks, Nick, for the nice and interesting talk. My question would be for the first part of the talk. You could show that you have really highly, or your method can predict the ferrocenium family quite well. My question would be, what are the boundaries of this method? So can you also do other lanthanides, other ligands? Because you mainly talked about just ring-based ligands and dysprosium as metal. Is it also possible just to extend that to other systems? And what are the predictive power for this, and how accurate would you be?
That's a really good question. So we haven't done a thorough enough survey to of say, let's say, regular coordination compounds or different metals or different parts of the periodic table to give you a definitive answer on how accurate it is. But there's nothing in principle to stop us doing that. I mean, we have done one calculation, we've published one calculation on a, let's say, coordination compound of dysprosium. It's one of these bis-tert butoxide type families, and they look okay. Again, these are high energy barrier single molecule magnets. So we haven't looked at many things that are not, highly performing ones, because of course that's how we get nice papers. But it is part of what we're looking at now into a big variety of different kinds of materials. So in terms of the applicability, there's no reason you can't do this for anything. The stuff I've showed you today was all gas phase. So of course, if you do have very flexible coordination geometries and you optimize a molecule in the gas phase, you're going to get something that's very, very far from reality. And so that's one problem, okay? So to combat that, you need to do the full crystalline optimization, which is what we are doing now as well. So we are doing this, so that's in principle soluble. Then you have the other part, which is accuracy of electronic structure. Because of course, we know with lanthanides, we have such big crystal field splittings, well, for dysprosium at least, that any uncertainties in the electronic calculations on the order of a couple or 10 wave numbers is insignificant compared to the crystal field splitting, so that we get, generally speaking, the right picture. Now, on the other end of the spectrum, if you start talking about, say, 3D metals, so start thinking about a qubit based on chromium or on copper, right, where you have tiny energies, tiny zero field splittings, fractions of wave numbers, EPR, real EPR transitions, or gadolinium even, right, where you have just the 7f electrons. Now you have a problem, because you have your calculations, which must be accurate for the zero field splitting on the order of sub wave number. And in order to get the vibration coupling being anywhere near relevant, you have to know very well that you're getting that right. So that's a massive problem. And so that's at the limit of CAST-CF level. So that would probably require a lot of study in terms of basis sets, active space sizes, dynamic correlation, all kinds of things to make sure that you can get that right. And we are looking at this. It's just a lot slower.
Question of time.
That's understandable. Good answer.
Okay. Olivier, you have a question?
Yes, a very naive question, perhaps. Can you use your vibronic calculation approach to assign precisely the luminescence spectra? In fact, the remaining transition in the luminescence spectra, because this is really an issue in this field.
Yes.
Generally,
let me
vibronics are the remaining transition.
Yes, let me very quickly, because I didn't put it in the slide, but I have the paper to hand, and I will show you a figure in the supplementary. This is all online. It's not published because referees take exception to a few things and think it's not that interesting, but hey-oh, we'll get around that. Let's have a look at a picture. But yes, we can certainly give information on those. Right at the bottom of the supplementary, as everything is these days. Okay, let me share screen. Okay, so this is the luminescence spectrum in the region. So this big peak here is our ground to first electronic, so KD1 excitation, oh sorry, KD1 to KD2 excitation. So that's about it's hidden by this, it's 470, it's off here somewhere. Anyway, these peaks here, these ones in green are the vibronic sidebands. And what you can see is that they actually really nicely line up. This E mode here is predicted to be quite strongly coupled and shows us this nice transition. There are lots of modes here that lie up really nicely. That one is bang on this peak. These ones are bang on that peak. We have a bunch here that are quite strongly coupled under this big peak, right? And you can see some shoulders here that might correspond to these ones as well. The only question I have is this region here, where we are predicting a bunch of strongly coupled peaks that we don't see experimentally. But I think overall, this is not a coincidence. that we have these things matching up. Also in terms of relative intensity, I think, once you take into account the integration of those peaks with the intensities we predict. So, well, I mean, these are not intensities that we're plotting. These are not transition intensities. Yeah. These are vibronic coupling strengths. But the stronger coupled ones seem to have more intense peaks, which is nice. So I think the answer is yes, but we haven't thoroughly gone into this yet.
Okay, this is really interesting. Thank you.
Lisa, Elisabetta, question?
Yes, thank you, Nick. It's amazing talk as always, beautiful work. So I'm really happy. So sorry, my camera is, oh, here I am. So I'm really happy to see that people do not try to remove CH bonds anymore from molecular magnets. It's wonderful. So as a summary of like everything together, so we basically have to look at two things. One is how strongly vibration is coupled to this particular electronic transition, or actually how this vibration strongly modulates a particular spin Hamiltonian parameter. And the other is how close this vibration to that particular electronic transition. So both have to be together, right? And when you were showing these graphs where the crystal field transitions are and where vibrations are they also like weighted by how strongly they're coupled to that transition or not?
So that's a good question. These S parameters are the same SJs that I was just talking about in the last part, and these are based on essentially the derivatives of crystal field parameters. So these are related to the strength of vibronic coupling. So essentially, you take this traditional crystal field strength parameter that was defined probably by Weiborn in the 60s or 50s or something like that, and you just use the derivatives to calculate this S parameter, and that seems to be pretty reliable in terms of representing a vibronic coupling strength. Because again, what does vibronic coupling strength mean when you have so many parameters in different states and blah, 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 blah. So we found this to be the most consistently reliable across different kinds of experiments so far. So that's what the heights of these blue sticks represent.
Okay, but it's not related to a particular transition.
No,
right?
No, that is not,
like
well, sorry, it's not related, it's related to a specific vibrational mode, but not a particular transition, correct.
Okay.
This is not the norm of the matrix element or something. You could of course plot all those for a given transition, but again, yeah.
So, and do I get it right that in Firm's spectra, you see not only those vibrations which are close, but also how strongly they are coupled to that particular electronic transitions that you're looking at? Or like, did I get it right or not?
I think this is my problem with selling this paper, is trying to explain the damn problem, because it's not a trivial one, I have to say, right? You get
all the trivial ones are solved in 60s.
Yeah, well, you know, it's all there if you do the quantum mechanics. It's just that it's not so easy to understand. So in the first thing with single molecule magnets, we're talking about vibrational modes must match electronic excitations, because in order to change the electronic state, you're absorbing a vibrational quantum or emitting a vibrational quantum. And
yeah, but if it's not coupled, it doesn't matter if it matches, does it?
That's true, yes. So we're now talking about different parts of the expression for single phonon transition rates, which is this. So if your coupling is this Hamiltonian matrix element is 0, it doesn't matter how close your energy is, you're still going to have a 0, right? Fine. But yes, it must couple, it must link the two states, but it also must be the right energy. And it must be the right energy because you are literally absorbing that vibrational energy to make the transition. So you're essentially going from a state where you have some occupation of a vibrational mode up here, and then you're reducing the vibrational occupation by 1 whilst you excite an electronic transition. That's what this says. You go up in electronic excitation and you lose a quantum of vibration for that mode. Right. That's standard spin phonon coupling talk. What we're talking about in firms is a bit different, because we are making a simultaneous electronic and vibrational excitation with a photon. So when I'm saying that we see firm's intensity when the vibrational energies match electronic states, that's not because they're being absorbed. That's because you have this sort of resonance in your Hamiltonian where there's a delta that matches your h bar omega. And if you do perturbation theory, you get this denominator. And so if your crystal field splitting matches, there's a resonance between a vibrational state in your Hamiltonian and an electronic state, this denominator goes to 0, and then this intensity goes through the roof. Of course, that's perturbation theory, so it's not real, but we can talk about that later if you want. But this is where you're making a simultaneous vibrational and electronic excitation. So we're going from, let's say, the lower part of KD1 and no vibrations up to the upper part of KD1 and 1 vibration. So we're changing electronic and vibrational quantum, and that the intensity of that transition as driven by a photon with energy h nu, which equals delta E plus h bar omega, right? So the resonance of the vibration does not equal, sorry, the energy of the vibration does not equal the energy of the electronic transition you are doing. It can be the electronic transition of anything, any other gap in your Hamiltonian. As long as there's a resonance, you get this kind of pattern.
But in that case, is it only the resonance that's important, or some sort of coupling also plays a role in the denominator?
Of course, the coupling is important. So in the numerator, F and G represent vibronic coupling strengths in this model Hamiltonian. And these essentially are related to the matrix elements of those crystal field parameters, for instance.
So it's really hard to link if those vibrations that manifest itself in firms are actually driving relaxation or not, because the physics is slightly different, right? Yeah.
Exactly. I am making zero connections between those 2 points at this part.
It would be nice to have one.
I know. But remember, the problem is the magnetic relaxation dynamics of this molecule are all 2-phonon. So I would need to do this, fully crystal phase, everything, all of the acoustic modes, right? Which in terms of, if you're looking at the acoustic modes, remember, these are very, very low energy, right? Vibrations. And they would occur, if you're doing intra-Kramer's doublet transitions, you would see only the acoustic modes here near 0. Of course, if you're doing inter, yes, you would have all the acoustic vibronic transitions right next to these pure electronic excitation. But again, that's really hard. That's a really hard region to split out. They could be there, but of course, what we also know is that the infrared dipole absorption intensity of an acoustic mode is so much lower than that of a localized mode, right? Because if you're just shifting the whole molecule, you don't change really the dipole moment. So you're not,
it's assuming the rigid molecule, but they're never rigid, so they are coupled.
Of course, and in the pseudo-acoustic region where you have, the different molecules in the units, primitive unit cell moving near each other, then again, they're non-zero. You do have changes in dipole moment, but they are far lower than the change in dipole moment induced by an actual bond stretch or something like that. So though the intensity of those infrared transitions on their own are going to be much lower. And also they're really hard to measure, because if you look here, there's an instrument. So this is transmission. We have 0 transmission at 0 energy. So there's instrument problems for even measuring these things.
It's a synchrotron alpha matter.
Yeah.
Okay, thanks.
Thank you.
Maybe I think Guillaume has the last question, and then you will close this session. So Guillaume.
Thank you, Boris. Nick, I would like to come back on your 2-phonon process. If I understand well, it means that you do not need the overlap between the electronic transition and the vibrational one.
Correct.
So it means that it can. But every time you have this kind of 2-phonon process, you have a shortcut and you have a relaxation that is fastened.
Remember, the Orbach thing is the rate of an Orbach process is traveling towards slow times exponentially quickly. Like it goes very, very fast, right? Because you have in a good single molecule magnet, you have gaps that are on, if I have a picture somewhere, hundreds and hundreds. So in the first dysprosocenium SMM, this is 470 wave numbers. So the occupation of a vibrational mode at 470 wave numbers, go and do the Boltzmann, your statistics are really, really bad as you start going cold. So this shoots down exponentially quickly, right? So you disappear so quickly that whatever's underlying is going to be there. So it kind of irrelevant to say it's going to be faster. It's like there's a time scale associated with this process, which is associated with essentially the dynamics of the lattice, the vibrational dynamics of the lattice, which is not trivial, which is why we don't have a clear answer yet. But yes, you do not have to have resonance.
Is there any particular symmetry that promotes or prevents this kind of two phonons process?
I don't know yet. I don't think so, because essentially you can take, because the dominant contributions of these modes are the very, very low energy ones, because we are at such low temperatures that the occupations must be sufficiently high that you can de-excite. Because remember, this involves simultaneous excitation and de-excitation of two different vibrational modes. So you must have an excited vibrational quantum of one mode in order to see it. And so you own this process is dominated by the very, very low energy phonons, because they have, near zero energy, non-zero occupations, even down to absolute zero, right? So that's why it's dominated by low energy phonons. And those are the acoustic and the pseudo-acoustic nodes of the solid state, which are essentially pseudo-rigid translations, rotations, tiny little things. And so it's very hard, and they couple all kinds of different motions, and they project onto local modes in very non-trivial ways. And remember, you can break, by doing, if you have a crystal symmetry, you have a crystal structure, the space group. Whenever you do a phonon, you're breaking the symmetry, right? And then you have different wave vectors which describe how the phonon maps onto different neighboring unit cells, right? And the periodicity of the lattice, and you break the symmetry. So certain symmetries are broken by vibrations anyway, and how these map onto the pseudoacoustic spectrum is really non-trivial, but it's a really good question.
Okay. Thank you, Nicolas. Is there any other questions or comments? Apparently no. So I will close the session. Thanks really a lot to the two speakers of today for their wonderful talk, and also for all the discussion we had. I think this is really missing to a lot of people, this kind of discussion. So it's very nice we can have it. And really, really thank you for all of this. And so the next webinar will be on the 24th of June with Rodrigue Lesquezec and Stephen Hill that will present their work. We don't have the title yet, but I will send you the information as soon as I will have it. Thanks a lot. So all the webinar has been registered, recorded, except the first 2 minutes of Kévin talk because I forgot it. So I will try to put it online for 1 or 2 weeks in order that people who were not able to attend could see it later. And again, I will send you the information. Is there nothing else to share from your side? No, it's fine?
Yep.
Okay, so thank you all and see you on the next webinar. Thank you again for the speakers. Bye-bye.
Yeah, thank you very much. Bye.